Welcome back. We have spent several episodes learning to eliminate a matrix down to its row-reduced form. Today we cash in. When elimination finishes, certain entries survive as pivots, the leading entries of the non-zero rows. The number of pivots has a name, the rank, and it turns out to be the single most informative number you can attach to a matrix. Rank decides whether a system can be solved at all, and if it can, whether the answer is unique or one of infinitely many. Today we define rank as that pivot count, derive the condition for a system to be consistent, and describe every solution at once as a particular solution plus the null space. We will isolate two clean situations, full column rank, which forces uniqueness, and full row rank, which guarantees existence for every right-hand side, and we will see that every linear system on Earth falls into exactly one of three outcomes: one solution, no solution, or infinitely many. Let's pin down rank. After you reduce a matrix to echelon form, count the pivots, the leading non-zero entry in each non-zero row. That count is the rank. What makes rank so central is that the same number shows up three different ways. It is the number of pivots. It is also the number of rows that are genuinely independent, meaning no row is a combination of the others. And it is the number of columns that are genuinely independent. The remarkable theorem hiding here is that the row count and the column count always agree. Row rank equals column rank for every matrix. For a matrix with m rows and n columns, the rank is at least 0, and at most the smaller of m and n, since you cannot have more pivots than rows or more pivots than columns. The columns that do not receive a pivot are the free directions of the system, and as we will see, those free columns are exactly where extra solutions come from. The first question for any system is whether it has a solution at all. We call a system consistent if at least one solution exists. To test it, attach the right-hand side B to the matrix A, forming the augmented matrix, and row reduce. The system is consistent unless elimination ever produces a row that is all zeros on the left but a non-zero number on the right. Such a row reads 0 equals some non-zero number, a flat contradiction, and it means no solution can exist. There is a clean way to say this with rank. The system is consistent exactly when the rank of A equals the rank of the augmented matrix. In other words, tacking on the column B must not create a brand new pivot. Geometrically, the picture is lovely. The product A times X is always some combination of the columns of A, so AX equals B is solvable precisely when B lies in the span of those columns, the column space. If B is reachable by the columns, you can solve. If it sticks out of their span, you cannot. Suppose a system is consistent. How do we describe all of its solutions at once? The key is the companion system with a 0 right-hand side, AX equals 0, called the homogeneous system. Its solution set is the null space of A. Here is the structure theorem, and it is one of the most useful facts in the subject. Find just one solution of AX equals B, call it the particular solution, XP. Then every solution is that particular solution plus some solution of the homogeneous system. In symbols, X equals XP plus XH, where A times XH is 0, so the general solution equals a particular solution plus the null space. The reason is a one-line calculation. If two vectors both solve AX equals B, then A applied to their difference gives B minus B, which is 0, so their difference lives in the null space. That means any two solutions differ only by a null space vector. One fix pins down the offset. The null space supplies all the freedom. Now let's split into the two clean special cases, starting with full column rank. A matrix has full column rank when its rank equals its number of columns. That is, every column gets a pivot. With a pivot in every column, there are no free variables left, so the homogeneous system AX equals 0 has only the 0 solution. The null space collapses to just the single point 0. Feed that back into the structure theorem. The general solution is a particular solution plus only the 0 vector, so if a solution exists, it is the only one. Uniqueness is guaranteed. The catch is that existence is not. Full column rank typically happens with tall, thin matrices, more equations than unknowns, where a given right-hand side may simply be unreachable. So under full column rank, there are exactly two possibilities, either one unique solution or no solution at all. What can never happen is infinitely many. The mirror image case is full row rank. A matrix has full row rank when its rank equals its number of rows, a pivot in every row. With a pivot in every row, elimination never leads an all-zero row, so the contradiction we worried about, 0 equals something non-zero, simply cannot arise. That means AX equals B is consistent for every possible right-hand side. Existence is guaranteed no matter what B you choose. This typically happens with short, wide matrices, more unknowns than equations. Here uniqueness is what is in doubt. If there are more columns than rows, some columns get no pivot, those are free variables, the null space is bigger than just 0, and so there are infinitely many solutions. The only way to also get uniqueness is if the matrix is square, with a pivot in every row and every column at once. So under full row rank, the outcomes are either exactly one solution, when the matrix is square and full rank, or infinitely many. The cleanest situation of all is a square matrix with full rank. When a matrix has the same number of rows and columns and its rank equals that number, full column rank and full row rank happen together, and so do their two guarantees. A pivot in every row means existence for every right-hand side. A pivot in every column means uniqueness. Put them together and you get the headline fact: a square matrix has full rank exactly when it is invertible, which is exactly when AX equals B has one unique solution for every possible B. The null space collapses to just 0, and the inverse matrix exists. This is the gold standard case the earlier episodes on the inverse were quietly assuming. The flip side is just as important. If a square matrix is rank deficient, rank below its size, which we also call singular, then it has no inverse, and a system either contradicts itself or has infinitely many solutions. What it can never have is exactly one. Full rank is the dividing line. Here is the whole logic on one diagram. Start at the top with the system AX equals B. The first fork asks, is it consistent? If the rank of A is less than the rank of the augmented matrix, the right-hand side forces a contradiction, and we land in the red panel, no solution, like two parallel lines that never meet. If the system is consistent, we take the second fork, which asks about the columns. If the rank equals the number of columns, full column rank, there are no free variables, the null space is just 0, and we land in the green panel, exactly one solution, two lines crossing at a single point. But if the rank is less than the number of columns, free variables survive, the null space has real directions in it, and we land in the blue panel, infinitely many solutions, drawn as a particular point plus an arrow of freedom along the null space. 3 panels, 3 outcomes, and rank is the quantity steering every fork. There is a clean accounting rule lurking here, and it deserves its own name. Every column of the matrix is one of two kinds: a pivot column, which gets a pivot during elimination, or a free column, which does not. Add the two counts and you must get the total number of columns. The number of pivot columns is the rank. The number of free columns is the dimension of the null space, the number of free variables. So rank plus the dimension of the null space equals the number of columns. That statement is the rank nullity theorem, and it is one of the load-bearing facts of linear algebra. Read it as a budget. The columns split their total between bound directions, counted by the rank, and free directions, counted by the nullity. Once you know the rank, the amount of freedom is forced. The number of free variables is just the number of columns minus the rank. More free variables means a larger null space, which means more solutions. The theorem turns counting pivots into counting solutions. Let's draw what a solution set actually looks like. Start at the origin. The navy line running through the origin is the null space. Every solution of the homogeneous system AX equals 0. It always passes through the origin, because 0 is always a homogeneous solution. Now the gold dot, sitting off to the side, is one particular solution of the real system AX equals B. The full solution set is the green line. Take the null space line and slide it over so it passes through that gold particular point. Notice the green line is parallel to the navy one but shifted. It does not go through the origin because B is not 0. That picture is the structure theorem made visual. Every point on the green line is a particular solution plus some homogeneous solution, and you reach them by sliding along the line with the free parameter. If the null space were a plane instead of a line, the solution set would be a parallel plane. The freedom in the homogeneous part is exactly the freedom in the full answer, just relocated. Let's see infinitely many solutions in action. We solve a system with 2 rows and 3 columns, first row 1, 2, 1, second row 2, 4, 3, right-hand side 3 and 8. Row reduce by subtracting 2 times the first row from the second. The second row becomes 0, 0, 1 on the left and 2 on the right. So there are pivots in columns 1 and 3. The rank is 2. But column 2 never gets a pivot, which makes its variable, x2 free. Set x2 equal to a parameter t. Back substitute, the second row says x3 equals 2. The first row says x1 plus 2t plus 2 equals 3, so x1 equals 1 minus 2t. Writing the answer as a vector, x equals the vector 1, 0, 2, plus t times the vector negative 2, 1, 0. That is exactly the structure theorem made visible, a particular solution, the first vector, plus a null space direction, the second vector, scaled by any t. Because t runs over all numbers, there are infinitely many solutions. Now a system with no solution. Take the matrix with first row 1, 1, and second row 2, 2, with right-hand side 1 and 5. Eliminate by subtracting 2 times the first row from the second. The second row collapses to 0, 0 on the left but 3 on the right. That row reads 0 equals 3, which is impossible, so the system has no solution. The rank test confirms it. The matrix A has rank 1, since its 2 rows are multiples of each other, but the augmented matrix has rank 2, because attaching B created a new pivot. The ranks differ, so the system is inconsistent. Geometrically, the reason is clear. Both columns of A are multiples of the vector 1, 2, so the column space is a single line. The right-hand side, the vector 1, 5, does not lie on that line, so B is unreachable by any combination of the columns. When the target sits outside the column space, no solution can exist. Finally, the clean case of a unique solution. Take the matrix with first row 1, 1, and second row 1, -1, with right-hand side 4 and 2. Eliminate by subtracting the first row from the second. The second row becomes 0, -2 on the left, and -2 on the right. Now there are pivots in both columns, so the rank is 2, which equals the number of columns and the number of rows at once. This matrix has full column rank and full row rank. Back substitute, the second row gives -2x2 equals -2, so x2 is 1. The first row gives x1 plus 1 equals 4, so x1 is 3. The solution is the vector 3, 1, and it is unique. Because every column has a pivot, there are no free variables. The null space is just the 0 vector, and the structure theorem leaves no room for any other answer. One pivot per column means one solution, full stop. A little history. The consistency condition we used, that a system has a solution exactly when the coefficient matrix and the augmented matrix share the same rank, is known as the Rouchet-Capelli theorem, settled in the 1800s as elimination matured under Gauss and others. The word rank itself, along with the word matrix, was coined by James Joseph Sylvester around 1851. It was Ferdinand Georg Frobenius, late in the 19th century, who proved the deep fact that row rank always equals column rank and built much of the theory connecting rank to the solvability of systems. In the modern view, rank, the null space, and the rank nullity theorem organize the entire question of solvability into a few clean statements. And these same ideas return again and again, in least square splitting, and data compression, and in the singular value decomposition, which we will reach later in this course. Let's recap. The rank of a matrix is its number of pivots, which equals its number of independent rows and its number of independent columns all at once. Rank decides solvability. A system, AX equals B, is consistent exactly when the rank of A equals the rank of the augmented matrix. Equivalently, when elimination never leaves a row reading 0 equals something non-zero, and when B lies in the column space. When the system is consistent, every solution is a particular solution plus a vector from the null space. The solutions of AX equals 0. Full column rank, rank equal to the number of columns, kills the null space down to just 0 and forces uniqueness, so the outcome is one solution or none. Full row rank, rank equal to the number of rows, guarantees consistency for every right-hand side, so the outcome is one solution or infinitely many. Together, every linear system lands in exactly one of three outcomes: one, none, or infinitely many. Next episode, for square matrices, a single number, the determinant, detects full rank at a glance. Today we learned to read the fate of a linear system off its pivots. The rank of the matrix is the number of pivots left after elimination, and it is also the number of truly independent rows and the number of truly independent columns. Those three counts always agree. Rank decides solvability. A system, AX equals B, is consistent, meaning it has at least one solution, exactly when B does not force a contradiction during elimination. In row-reduced form, you must never end up with a row of all zeros on the left equal to a non-zero number on the right. When the system is consistent, every solution has the same shape, a particular solution plus any solution of the homogeneous system, AX equals 0, which we call the null space. If the rank equals the number of columns, full column rank, there are no free variables, the null space is just the 0 vector and the solution, when it exists, is unique. If the rank equals the number of rows, full row rank, the system is consistent for every right-hand side. Put the cases together and every system lands in exactly one of three outcomes: one solution, no solution, or infinitely many. Next episode, for square matrices, a single number, the determinant, flags full rank instantly. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.